Hi class, this is number 7 on 5.2. The duration of a professor's class has a continuous uniform distribution between 50 and 50.2 minutes. If one class is randomly selected, find the probability the professor's class duration is between 50.2 and 50.9 minutes. So when something is universally distributed, that means that it's the same. And so a probability distribution that is universally distributed, if we saw one written out as a table-like form, it would mean for whatever variable, for every value of x, the probability is the same, 1/6. It's like, and so a good example of a uniform distribution, a probability experiment that has a universal distribution, continuously uniform distribution, is the probability experiment of rolling a dice. Right? When you roll a dice, what's the probability of rolling a 1? 1/6. What's the probability of rolling a 2? 1/6. What's the probability of rolling a 3? 1/6. What's the probability of rolling a 4? 1/6, right? So and what's the probability of rolling a 6? 1/6. So see how it's uniform? The probability is the same for every single different outcome of our probability experiment. So that's what's going on with this situation. Between 50 and 52 minutes, and let's just round to 1 decimal place. Focus on 1 decimal place right now. That means that his lecture is equally likely to finish at exactly 50 minutes, or between 50 and 50.1 minutes, and between 51 minutes and 50.2 minutes, and between 50. Let me write it out. It's equally likely to be to end between 50 and 50.1 minutes, and 50.1 and 50.2. Oops, it's supposed to be 50.1 and 50.2. So you're equally likely for that lecture to end, and we're just going to be accurate to 1 decimal place, between any of these time periods. So this is kind of similar to like that problem where you have like a spinner, and let's say you have 12 things that it could possibly equally spaced things that it could possibly land on. What's the probability that it's going to land on any one of those 12? It's 1/12. Right? Because there's 12 spaces that it could possibly land on. So we need to count the number of spaces between 50 and 50.2, and we're just going to count them just accurate to 1 decimal place. And that'll be like for us, it'll be like, we'll call this one 50.1, and we'll call this one 50.0, this one 50.2, this one 50.3, right? And we have the same all these are equally likely. So how many of these would we have on that wheel? Between 50.0 and 50.2. How many of these numbers would we have on the wheel? That's the question. Because in order for us, just like we need to know how many spaces are on the wheel to figure out we have a 1 out of 12 chance of landing on one. We need to figure out how many spaces are between 50 and 52 because all of them are equally likely to land on, and we just need to know how many of them are there. So that's one way of looking and thinking about this problem. So I'm going to draw the picture. Well, let's it's let's draw a picture on the x-axis. And let's say between 50.0 and being, I might make more space here, 52.0. Well, isn't there 10? There's 10 between, and this will be 51 exactly 0.0. But this will be 50.1, 50.2, 50.3, and I'm not going to be able to fit all these in here. I didn't make them big enough. Maybe I should only go to like, only put a few in here. Maybe I'll just make halfway in between 51.0 and I'll put the 50.5. Halfway in between 51.0 and 55.2, I'll put 51.5. Okay, so then we can kind of count the number of spaces in here. It seems to me like there's going to be 10 between 51 and 52, right? There's going to be one right here between 51.0 and 51.1, right? And then one between, 51.1 and 51.2 and so on. But we can break this thing up into 20. I believe it'll be 20. It's between 51.0 and 51, that'll be 1. 50.1, that'll be 1. And then all the way up to 50. And then, see, I think we're going to have 20. So that would mean that if we have 20, that would mean that the probability of us landing on any particular one, if we want to think about it in this situation, is 1/20th. And so the height we could make the height of this rectangle 1/20th. And so if we subtract, we just have to make sure now, if we subtract 52, then we find the width here, 52 minus 50, which will be 2 times by the height, that we should get, one whole, which at this moment we're not going to count one whole. Okay, this is just a distance of 2. Okay, hold on. Let's not go with that on that train of thought. Hold on. Let's go this way in this direction instead. Okay, so let's focus on finding the area over 50.2 and 50.9, which would be 50.2 would be like right here. That'd be the rectangle above 50.2 and all the way to 50.9, which would be like right. Oh wait, no, I'm wrong. This is the wrong spot on the graph. 50.2. Of course. Oh wait. There we go. 50.2 is right here. I'll call this 50.1. That's probably 50.2 right here. All the way to 50.9, which is over here. how many little rectangles is that? If I separated everything by 0.1, then how many little rectangles is between 50.2 and 50.9? So I'm going to subtract, I'm going to find the area and the distance over here. So 50.9 minus 50.2 is 0.7, or importantly for us, and I'm not paying attention to this decimal, I'm just paying attention to there was 7 rectangles here. So I'm kind of approaching this problem a little bit differently. I'm not considering the decimals. I'm just thinking of there being 7 rectangles are located here. So mine are a little thinner, I think, than maybe I could have done this problem. But anyways, there's 7 rectangles right above between 50.2 and 50.9. And so, and each of them have a probability of 1/20th. So we would say 1/20th times by 7 to find the total 7/20ths, to find the probability between 50.2 and 50.9. So let's check it. 7/20ths. And let's find and let's get yes. Yep, that's exactly it. It's 7/20ths. Yep, that's exactly it. So I kind of broke this rectangle. Uniform distribution means it's a visual representation of the distributions that the P of X. It's a graph. Of the probability distributions that we saw in our earlier sections, and now the only thing that's different is that they have made bar graphs that are the height of the probability, the P of X. So, and the variable X is along the X axis, and then the height is along the Y axis. The probability is according to probabilities. And in a uniform distribution, this height is uniform. It's the same height, the same probability for every single thing on that. Every single possible outcome has the same probability and same height. So the graph always looks like this rectangle. Well, you have to think about it as like, okay, well, now everything's equally likely occurring, so let's just add up the number of things there are and then divide by the number of things. In this case, there was 20 0.1 time limit section, 0.1 time spaces between 50 and 52, and they all were equally likely. So I knew each 0.1 was worth a probability of 1/20 of happening. So I said, hey, we have 7 of those between 50.2 and 50.9. So I hope that helps you. We probably could have done this problem differently. But I think this is probably one of the easier ways to do it. All right, have a good day. Bye.